This is a video about the Hall effect. So the Hall effect is something fairly interesting. If I've got a piece of semiconductor and I run a current through it, so maybe I am clipping to the front of this and, clipping over here. So if I run a current through this thing, there are two possibilities of what's really going on. We have talked about current being the direction of positive flow, but we have also talked about how it's not the positives that flow. Semiconductors fall into two categories in certain ways. There are p-type semiconductors, or there are n-type semiconductors. If you go into semiconductor science, you'll find that semiconductors fall into many categories, but p-type and n-type are two major categories. What these mean: p-type has positive charge carriers. That's why the P. And n-type has negative charge carriers. Details aside, you can think of it this way. I either have positive charges to get a current going to the right. I either have positive charges moving to the right, or I would get a current to the right if I had negative charges moving to the left. Both of those would give me the same current. So then the question becomes, which one do I have? If I've got the positive charges moving to the right, that's the p-type semiconductor. If I've got the negative charges moving left, that's the n-type. So I'm going to do this assuming for a moment that I have a p-type semiconductor. And this is what the Hall effect is all about. If I put this in a region with a magnetic field, so maybe I can put a magnetic field this way, perpendicular to the direction of current. Then if I have positive charge carriers moving to the right, with a magnetic field into the screen like this, they are going to experience a magnetic force that points upward. So what that looks like is these particles, I'm going to do a little bit of erasing. These particles are going to be diverted upward. Now, that's the first particle. So now there's a particle here. When the second particle comes along, so I'm going to get rid of this for a moment. When the second particle comes along, there's already this positive charge up here. It's going to get diverted also in the same way, but it sees this positive charge, so it might not get diverted exactly the same way. Now I've got a positive charge over here. So on for a little while, until I have this buildup of positive charges on my top plate. Once I have this buildup of positive charges on my top plate, I mean all along, but now that I've got this buildup of positive charges on my top plate, top end anyway, I am building up an electric field. Now this might remind you of the velocity selector because it's exactly the same thing as the velocity selector. At some point or other, these particles, the magnetic force wants to divert them upward, while the electric force wants to divert them downward. And so they just pass through. But in the meantime, this top plate is now positively charged. We can write this bottom plate as negatively charged or keep it neutral. It doesn't really matter. The big thing is I have this higher potential up here and a lower potential here. or the top is higher than the bottom. It doesn't matter where the 0 is. I have a potential difference with the top being positive and the bottom being negative. This is for positive charge carriers, and this thing we call a Hall voltage or a Hall potential. So now let me look at what happens if I've got negative charge carriers. So I will label this thing, this top one, as P-type so that we can keep it there. And we'll look at N-type separately. An N-type will do this. We've got a current that goes this way, and we've got our same magnetic field. So now, instead we have these negative charge carriers, and they are moving in the opposite direction. They have to be moving in the opposite direction because a negative charge moving to the left is mathematically equivalent to a positive charge moving to the right. So let's see what happens. If I've got this negative charge moving to the left, then in a region with a magnetic field that points into the screen, I'm going to use my left hand because it's a negative charge, and I'm going to find that this gets a magnetic force that points upward, meaning it's going to get diverted upward. So now I've got a negative charge here. The next charge that comes in has the same thing happen, and I'm going to get eventually a buildup of negative charges on top, which means the top plate will be at a lower potential than the bottom plate. Remember, you can think of potential kind of like elevation. So it doesn't matter that there aren't positive charges here. We are farther downhill than the bottom plate. So we can think of it as plus and minus, or as plus and more plus, or minus and 0, whatever you want. So this top plate gets a negative potential, and the bottom plate gets a relative positive potential, meaning now my Hall voltage is negative on top, positive on the bottom. This is an N-type semiconductor. Now there are different things that we can do with semiconductors, things that we can do to find out what kinds of properties these are going to exhibit and everything, but the big thing that you need for this course, the only thing that you really need for this course, is to be able to see from this field, or from this setup, am I looking at a P-type semiconductor or an N-type semiconductor? And that's it.